Hi everyone, I'm Tom Trey Holmes, and this is another video in the Retro Computing Archaeology series, a series of videos dedicated to accurate preservation of archaic retro computing knowledge for future generations. This particular video addresses what has been found recently, which is known to be the earliest copy of 86-DOS known to exist at this present time, that is, as of January 3rd, 2024. 86-DOS was the operating system that was originally written for the Seattle Computer Products Gazelle computer, and it was ultimately chosen by Microsoft to be the basis for what would become PC-DOS for the IBM PC, and licensed to other IBM PC compatible manufacturers as MS-DOS. So this particular product holds a very, very profound importance in computing history, and it is absolutely wonderful that this has been found. But the videos that have been released thus far have been just very terse walks through kind of, okay, booting it up, here it is, okay, it's great, this exists, and here's a link to it so that you can download it and run it in SimH. But I wanted to kind of go into it a bit further and show the tools that are actually on the disk and to use them in context. So let's say basically using the following scenario. You just got your brand new SCP Gazelle, you've got SCP DOS, you've got a handful of existing bits of CPM source code that you want to take and convert over to 8086 to run and use on your shiny new machine. This is how we do it. But before we do that, we'll actually take and go a little bit into what this actually is from an overview perspective. If we actually take and go to the link that it was actually given out, you'll see that we have a link here on Internet Archive, and we have basically instructions on how to basically set it up using SimH so you can run it. The reason being is that this doesn't run on a typical IBM PC computer at all. And in fact, if you're eagle-eyed enough here, you'll notice that this is actually not a 5 1/4 inch disk, but this is an 8-inch disk. So what was the Gazelle? Well, the Gazelle was a microcomputer that was produced by Seattle Computer Products. Seattle Computer Products was a hardware company that was originally established to make memory boards for S100 based machines. Well, what are S100 based machines? Well, I won't go too far into that. Look up the Altair 8800 and go from there, because that's where this standard actually was sprang from. And the standard for building the cards, their size, and how they connected together was called the S100 bus. And in a very short order, since its inception in 1975, the S100 bus was quickly adapted to service a whole bunch of different CPU types and even bus width types, going all the way up to 16 bits typically. And because everything used the same standard here, it meant that you could combine a whole bunch of different memory boards, input and output boards, and CPU boards to build the machine that you wanted to use. It was ultimately one of the first successful microcomputer architectures. And the Gazelle was just one of many hundreds of available S100 machines. This one was particularly special because it was built around an 8086 CPU card and support card that Seattle Computer Products had actually taken and produced. And if we actually take a look here, we'll see, first and foremost, that's not an ISA card, that is S100. That's 100 pins down there on the bus there. And this is just the CPU with its supporting circuitry just for the CPU part of the card. To build a full computer, you actually needed the support card as well. And the support board gave you basically a console and a console port for attaching a serial terminal for your console, and a few additional ports, some timers, interrupt controllers, basic I/O, just enough to build a basic computer around it. But you also needed memory, and the Gazelle could actually support up to a megabyte of memory. And that was definitely possible because there were 18 slots on the Gazelle motherboard, and you could put a whole bunch of different memory boards in. And because this machine could support a full megabyte of memory, unlike the original IBM PC, Gazelles were actually used at Microsoft for the final linking process for building MS-DOS up until version 5.0 of the operating system. So what do we need to actually run this? Well, to take and push this across here, what we actually need to run this is a copy of SimH, and we need to configure that copy of SimH for our purposes. We look at the configuration file for SimH here, we'll see a couple of things. And this file was contributed into the public. It's a wonderful place to start to take and build your own Gazelle using SimH. It works with the current version of SimH, without any changes. But as we can see right here, we have a series of commands which go into SimH to configure all the various pieces that we need. We need to set the CPU to 8086, but we also need to take and put the SCP Monitor in 2 locations on the system. We also need the serial port, because we need we also need a console for 86DOS to work in, because there's no graphics card, there's no display card, so we're having to take and go out a serial port to a serial terminal to provide our input and output for a console. We also need a Cromemco 4FDC disk controller in this case, but we want it with the RDOS ROM disabled. Well, what is that? If we actually take and go back here, we can see what this part is. This is a very common S100 floppy disk controller, very capable. You could have up to 4 floppy drives on a single controller here. And they could be single density, they could be double density, any combination of the two. You'll notice that this card has an RDOS ROM here. This is written in Z80, and it provides file system routines for bootstrapping and getting the board running on Z80 based machines. This is not a Z80 based machine, it's an 8086 based machine, so that ROM actually needs to be disabled. But we do want to take and enable the floppy disk controller bits. And we want to set the floppy disk controller type correctly so that we can boot the resulting disk images. On the first floppy drive, we have our 86DOS image, and we have what's going to be a blank disk image over here in drive B for now. We're going to take and fill it up in just a moment, but that's going to be where we copy our data from over to QDOS. We then take and start the monitor and bounce from that point. So once you do that, I've already done it here, it loads up, and then we have our monitor, and if we do B to boot, we go into 86DOS right here. And this is 86DOS right here. You'll see that the copyright date is 1980. This is very, very early in 1980, and long before the IBM PC was released, which coincidentally was August 12th, 1981. So this is a bit before that. You'll also notice some other interesting bits and pieces here. First and foremost, you'll notice that there are no date or time stamps. They don't exist. and they're not here. But unlike what some people have been saying here, the file system format that is on this disk is, believe it or not, it's FAT. It's file allocation table. But it is the earliest known form of 12-bit FAT known to exist. And the directory entries currently are not long enough to support date or timestamps. And you'll notice that the file size is also not shown here as well. You'll also notice that the prompt command is a little bit different than what IBM would have ultimately specified here, with it being an A: command. And on this disk itself, we have a handful of different things that we are going to use as part of our smoke test here. Of course, we've got the command interpreter, but we also have an interesting tool called RDCPM, which can read files from CPM disks to copy over onto our FAT format disk. This is important because QDOS has no way of natively reading CPM format disks itself. We also have a loader called hex2bin, which will be used after we do our assembly to turn our resulting assembled program into a workable binary program. We also have the Seattle Computer Products assembler here. This was not written by Microsoft. This is actually the assembler that was written at Seattle Computer Products here. We also have a program called trans, and this program right here takes Z80 source code and converts it into 8086 source code. Notice I said Z80 source code, not 8080. It is not an 8080 translator. It does not know anything about 8080 instructions, and it has absolutely there's no concept for any of it. So really, there's no way that you can't use it to convert something that builds with the Digital Research CPM assembler directly over. You have to convert that into Z80, and then you can use trans here. And even then, there are slight differences, as we'll see here, that we have to deal with when we do our translation. There's a sys program here, which is used to copy a bootable copy of the system onto another disk. There is the line editor here called Edlin, and they provided a chess program here, just as a demonstration, ostensibly. And I find this very curious, especially because this came off an original distribution copy of the disk. You'll see this is an original label, so maybe this was copied on after the fact. Not sure. But if we take a look at it, you see it really doesn't say much more than just how to enter moves into the game. So now comes the interesting part. How do we get our source code onto here so that we can assemble it? We can just as easily enter it here, but I'm actually going to take and use the rest of this video to take and write a small piece of software over in CPM, which I have over in this window here, and I will take and copy it over so that it can be put onto a disk image and used using RDCPM over here. We'll have a third window available here that serves as a modern terminal window here to show the disk conversion process. So with that, let's get started. We are indeed over here in a copy of CPM, and we've got all sorts of stuff that we're working on over here, but we want to make sure that our environment works. So for that, we'll just do the simplest little program that we can think of here using the line editor that's built into CPM. Well, not built, just part of the distribution disk. And we'll write a little program called hello.asm. Okay, it's a new file. We'll hit I to insert. And through the magic of cut and paste here, I'll actually take and bring our original program over here so we can assemble it to make sure it's okay. Of course, now we'll hit Control Z and we'll exit and edit. Now, if we actually take at this point and use the assembler on this program, we'll see that it assembles just fine. This is the standard CPM assembler from Digital Research. It has no relocatable abilities. It has no macro abilities. It's just the plain assembler. But it generates a few files for us. It generates a listing, which we can check against to make sure that everything is okay, because we see where everything is being assembled to and what is being assembled to those locations alongside our source material right over here on the right. But we also have an Intel hex format here. Now, if you want, you can do a little look up on what Intel hex format actually is. And it's a fairly standard format that was intended to be put onto ASCII mediums such as paper tape, or put onto magnetic tape, whatever, to be sent to an EEPROM burner or to some medium to basically output a binary at some destination machine. So you would do development on a system like this, output your hex file, and that would be your tape out to go to your EEPROM, to go to your final destination. In this case, this program is intended to be run here, so we can actually use the loader here, that's load com, to take that hello hex file and output it to a com file here, which we can then run. Of course, we run it right here, bam, there it is. And we'll see there's really not much going on here. We have basically all CPM programs need to start at 0100. We put a 9 into register C. That is the system call for printing a string ending and ending with the $sign. We need to put register D to point to our message. And then we need to call, we need to jump to location 5, which contains our BDOS call, which says, okay, this is an operating system call, go here, do it, and then come back. Once we come back, we immediately take and call 0 to cold start and jump back to the operating system. There are a few different ways to do it, but I chose this way here. Finally, we have the message down here below that is referenced as the message label here, which gets put into register D here. So we can see this assembles, it works, it does exactly what it's supposed to. Now, as I said before, the trans utility has no way of dealing with 8080 format instructions and wants Z80 instructions instead. There were plenty of tools to be able to do this. One of them being, for example, Ztran, and failing that, you could always do it by hand. And it goes ahead, pulls the data in, does the Z80 translation, and if we take a look at the resulting file that it created, we can see that it's mostly the same, just the instructions are a little bit different. These are in Z80 format instead of LXI or MVI. It's a general load instruction. The call instruction is the same, and it changed the DB instruction here to defB. This just happens to be compatible with Z80 ASM. Okay, great. We're going to have to deal with that when we bring it over, but no big deal. Now we have this file here. Now we need to take and move this into a disk image. We need to move this into a disk image because SimH only deals with disk images attached to the drives. And these act like the physical disks, except instead of writing to physical disks, we're dealing with files that contain all the various sectors inside the disk. So how do we do that? Well, we start by creating a blank file that has the correct number of bytes to correspond to our disk image. How big is that? Well, if we actually take and take a look at disk formats that we need, the disk format that we want is a very standard format called IBM 3740 format. Now, this is partially correct here. We have 73 tracks with 26 sectors storing 128 bytes per sector. What they don't tell you here in this little paragraph is that there are 4 tracks that IBM specified as spare tracks. Now, most people didn't actually treat these as spare tracks. They just formatted the whole thing as 77 sectors. Now, what was the IBM 3740 here? And where did this whole come from? Well, if we actually take a little aside here, go look up IBM's 3740 sometime. And that is an interesting little rabbit hole to go down. It was the first major popular floppy disk format, and it was part of a key punch system. But because these disks were so prevalent and so popular, they were adopted by just about every computer system that had an 8-inch disk drive. And for CPM adopted this disk format and the logical format of the data on that disk as the basis for the CPM file system. So, as we said before, 77 tracks, 26 sectors, 128 bytes per sector. And if we do a little bit of calculation, we come up with that's 2002 sectors at 128 bytes per sector, 256,256 bytes. So all we really need to do is make a file that's going to be zeroed out at first, because we're going to put the appropriate formatting in it in the next piece here. Write it out. Okay, great. We're good to go. And now I can then come in here, and we've got this large file right here. It's currently full of zeros because we used dev0 to make the file. Well, no problem. I can take and select, and I'm going to select the entire range of the file here. And we're going to fill this file with the fill byte of E5. E5 is the standard fill byte that IBM used during their acceptance test because it's the most difficult byte to modulate using the frequency modulation standard that IBM developed. So it made sense for them to use this as their fill byte. So we're going to fill the whole disk with E5s here. At this point, this disk is now ready. You could take this, put this onto an 8-inch disk, and CPM would go, oh, this is an empty disk. It has no files on it. So for the next piece, I'm actually going to take and use the CPM disk tools. And I'm going to place that copy of the hello Z80 file onto this disk as hello.asm. It doesn't need to be hello Z80, just hello ASM. Boom. And if I do a CPMLS, we'll see it. There it is sitting on that disk. And in fact, if we actually take and go into CPM data here and scroll down just a little bit, we'll see a directory entry for hello ASM right here. And we'll see our data right there, ready to go. Along with, very curiously, because CPM is dealing entirely in sectors, if there's a remainder of data waiting to be written for a whole sector, then the last byte is padded out to fill out the entire 128 byte sector. So that's a Control-Z character all the way down to the end of the sector. So there we go. It's ready to go. And if we actually take a look real quick at 86DOS, we'll actually see that our configuration file already has the definition for it right here, and it's placed into the second floppy drive. So if I take now and I'm going to go ahead and hit Control E to stop the simulation and restart. And we're going to boot again. Have to be uppercase. What happens if I try to take a look at drive B with this CPM disk sitting in drive B? It's going to look like garbage because the file format that's on the drive B, the file system that's on drive B, is not FAT. It is not FAT. It is the CPM file system. Again, 86DOS has no way of reading CPM disks directly, which is why you need the RDCPM program. And this program is very rudimentary here. It's not interactive at all. You must know exactly what you are copying off of your CPM disk onto your destination disk. In our case, it's the hello.asm as hello.asm. It doesn't even, this particular version of the program is so early, it doesn't even give you an indication that it was successful or not. The only indication that it might have been successful is that you've got a hello ASM file sitting on your DOS disk now. If we take a look, we can see our Z80 assembler did make it over, safe and sound. Okay, great. Now we need to take and translate that to 8086 code. And we use the trans command for that. Recall that there's a trans command up there. Okay, great. Hello.asm. Z80 to 8086 translator, version 2.0, translation complete. Now, again, it doesn't give you any errors or any indication if something went right or went wrong. Instead, it opts to do that in line inside your file as it overwrites it. As we'll see here in just a moment. But we can see now, up top, we have the Z80 code here, and down here on the bottom, we have our 8086 code here. It did a rough instruction translation from Z80 to 8086. And we'll see right here, because the defb is not accepted as a valid pseudo opcode. It doesn't know what to do with this, so it throws an error, so that you can deal with it, because the assembler is not going to be able to deal with that. We need to change that. And to do that, we'll use the Edlin tool. Oops, wrong window. Focus follows mouse, gentlemen. Okay. Edlin. Hello.asm. And this version of Edlin is so early, it doesn't even say, oh, this is a new file. Oh, this is end of input file. No. It's just poof, right to the prompt. Great. Do an L to list, and we can see our error message right there. And if I take and I'll go ahead and delete that error message, because it's actually going to muck things up if I don't. And I'll edit line 6 here and turn this into that. And if I take and do a 1L, we'll see, okay, there is our there's our change right there with the active cursor sitting just at line 6. Looks good to me. Look good to you? Okay, great. We'll use E to exit and edit, save our changes, and it helpfully created a backup file for us. We don't really need it, so I'll use the erase command to delete it. There is no del command. That would be added by IBM later. So there's our file right there. It's translated, and now I can turn right around and use the assembler to assemble the result. And we'll see right there, there's the 8086 assembler version 2, no error count. And just like with the DRI assembler on CPM, we also get a listing file right here in a similar format. And we get another Intel hex format, but this time with the binary and 8086 with 8086 instructions instead of Z80 instructions. Okay. So to use this, we need, instead of using the load command in CPM, we need to use the hex2 bin. Doesn't tell us anything, it just does it. And there's our hello com. And if we run it, there it is. Now, this is where I did it this way to actually try to address something, you know, what some people consider to be the elephant in the room. And that is this persistent anecdote that QDOS, 86-DOS, MS-DOS ripped off CPM. No, it did not. Thankfully, because the source code is now available on GitHub for both MS-DOS and CPM. You can now take and cross-reference the two. And you will see that, no, there is no source code copied between the two. Last but not least, because not only because the CPUs are totally different in the first place, but different file systems, FAT versus the CPM file system, and the fact that there is actually a whole different programming structure that you're supposed to use going forward. For writing software. And there is absolutely a ton of great material over here on BitSavers showing how you write software, including the system functions. Now, the system functions here, these are derived, you know, you can argue that these were derived from publicly available documentation as to the order that they're in, the parameters that they take. But you'll see right here that for these, the register order and whatnot, even though you can pass in the parameters to some of these functions using CPM register order, they really wanted you to use the correct registers here, using AL, using AH and AL to pass in the system call and some basic functions, all the parameters. Larger parameters in DX, CX, etc. But also different ways to exit the program. For example, you have interrupt 21 function 0, which is terminate, but there's also interrupt 20H for terminating an application, for example. There's a few different ways you can do this. So it's very persistent that it was like, oh, they borrowed code from CPM, they just ripped off code from CPM to do this. No, they did not. QDOS and 86-DOS, with the links that I provide in the description here, you'll see that 86-DOS was a re-implementation using publicly available documentation. So with that, I'm actually going to end this here. And I hope you guys actually enjoyed this here. So trying to see these various different bits and pieces in context. In fact, actually, I'll show kind of a weird little bit of irony here. The system call method that was done here of using the CPM compatible entry points persisted all the way up through the various versions of MS-DOS. Like, for example, I will go ahead and we'll just bounce right into... let me find real quick. Give me just a moment. Okay, I've booted up just really quickly a copy of PC-DOS version 2.10 on an IBM XT. Version 2 was actually a complete rewrite of MS-DOS from version 1 but they actually still kept the IBM PC compatibility layer here, which we'll see. In fact, I will actually take and do the same program here, just quickly writing it into debug, and we'll just go ahead and do it here. So move, hold on a split second. Okay, move DX. Sorry, move DX, that'll be a 011B, 011B. Call, you can still call BDOS, but actually I need to change to be 10B and unassemble real quick to check. Looks good to me. Now I will take and set 118. Okay, great. RCX, 18 bytes, 18 hex bytes, and just write out the results. And yeah, even though there is no CPM code inside of here, the CPM calling methods are still maintained. So this is the source of why this persistent rumor exists here. So with that, I'll actually end the video here. I hope you guys actually found this enjoyable, and I will be making more of these in the future. So until next time, guys, have fun.